If I have a picture of a dog and I want to search the internet for pictures that look like that dog, how can I do that? I need to make an algorithm to build an index of all the pictures on the internet. That index can define the different features of all the images. I can find mathematical features in each image that describe that image, and then I can sort those images based on those features that I define. The mathematical features can be represented by a matrix of numbers. Then I can run the same algorithm on that picture of my dog, and this will make another matrix of numbers. I can compare the matrix that represents my dog to the matrices of all the pictures on the internet. This is what Google and Facebook do. And we covered this topic in our episode about similarity search a few weeks ago. Today, we evaluate a similar problem, searching images within Squarespace. Squarespace is a platform where users can easily build their own website for blogging, e-commerce, or anything else. Neel Vadoothker is a machine learning engineer at Squarespace, and he joins the show to talk about how and why he built a visual similarity search engine. And if you like this episode, we've done many other shows about machine learning. You can check out our back catalog by downloading the Software Engineering Daily app for iOS, where you can listen to all of our old episodes and easily discover new topics that might interest you. You can upvote the episodes you like and get recommendations based on your listening history. With 600 episodes, it is hard to find the episodes that appeal to you, and we hope that the app helps with that. We've got the Android app on the way, and we'll let you know when that's available. In the meantime, I hope the iOS app is useful for you. Life is too short to have a job that you don't enjoy. If you don't like your job, go to hired.com/sedaily. Hired makes finding a new job enjoyable. And Hired will connect you with a talent advocate that will walk you through the process of finding a better job. It's like a personal concierge for finding a job. Maybe you want more flexible hours or more money or remote work. Maybe you want to work at Facebook or Uber or Stripe or some of the other top companies that are desperately looking for engineers on Hired. You deserve a job that you enjoy because you're someone who spends their spare time listening to a software engineering podcast. Clearly, you're passionate about software, so it's definitely possible to find a job that you enjoy. Check out hired.com/sedaily to get a special offer for Software Engineering Daily listeners. A $1,000 signing bonus from Hired when you find that great job that gives you respect and salary that you deserve as a great engineer. I love Hired because it puts more power in the hands of engineers. Go to hired.com/sedaily to get advantage of that special offer. And thanks to Hired for being a continued long-time sponsor of Software Engineering Daily. Neel Vadoothker is a machine learning engineer at Squarespace. Neel, welcome to Software Engineering Daily.
Hi, nice to meet you.
Today we're going to talk about some back-end engineering, machine learning problems that you have worked on solving at Squarespace, but let's start by giving some people context on what Squarespace is if they're unfamiliar with the product. Explain what Squarespace is.
So if you listen to podcasts, you're probably already familiar with Squarespace. We sponsor a lot of podcasts. To give you just an overview, we're a website that makes other websites. So Squarespace.com is a company that was started, I guess, like 13 years ago by Anthony Casalena. And basically, he's an engineer, and he basically built a company that allows you to log on and you can build whatever website you want to. So a lot of our customers are commerce customers who have small stores or restaurants or personal portfolio websites. We have a lot of photographers on there as well. So basically, you can create your home on the web using Squarespace, if that makes sense.
Right. And I think key to this is that there are a lot of images across Squarespace, across all these, you can make a personal website, and there's a lot of images that people add to their website because there's a real emphasis on design and imagery.
Right, right. That's basically the major differentiator for us against our competitors. We are very, very focused on design. So we like to sort of make sure our customers have the ability to add a lot of images on our websites. And so all of our demo content, if you ever go to squarespace.com and you look at our templates, you'll see a lot of very high quality images that are well taken. So we want to sort of push that aesthetic on people as well, if we can.
So across all of these different personal sites that people have, there's a lot of data in aggregate. Can you describe the data engineering infrastructure?
Yeah, so my team specifically, does not do all the data processing, but I can still go through that for you. So we essentially, if you think about what is a website is basically the HTML on the website, and all the different, pieces of data that go on are essentially can boil down to text and images and audio files or video files or whatever else you want to put on your site. So the main data the data processing and pipelining systems that we have are basically to store all of our customers' individual data into little blocks on our website, and then reference our images stored on our own internal storage systems, so that when you basically load a website using our site server our web serving system, you can just access all of those little blocks and build out or then display each page at a time. Is that what you're looking for?
Yeah. Well, mostly I kind of wanted to know if there is any infrastructure in place. Because, to give people some context, in Squarespace, everybody's got their own little sandboxed page. Like I make jeffmyersonphotos.com, and it's just kind of like my little photo website. And it's not really, at least from the outside, connected to other websites. This is not like a social network exactly, right, at least on the outside. So probably there's no real reason to gather information, aggregate information to build some sort of social graph among the different websites, at least not as a main priority. So that's kind of what I was prodding at is there any centralizing infrastructure built to gather all of the different data? Because we're going to get into, there's all this this machine learning stuff that you're working on. And so, eventually we're going to talk about how you gather those data sets. So I just wanted to talk up front to see if there's any data engineering infrastructure built for that.
Yeah, so we actually have our own scraping system that collects the raw HTML from outside of our internal systems, that grabs all the HTML, so we just have the machine learning team has its own system that grabs all the data and stores it itself in our own internal HDFS. So internally, we use MongoDB pretty heavily, and so a lot of our data is stored there. The files don't stay specifically, the image files, for example, or the video files don't stay specifically in MongoDB. So we store those separately on a separate file system. But when you're right that there's not much reason, except for, analytics or for machine learning work, that we need to aggregate data across every single website. They're all sandboxed. But we can still do things like that because we essentially copy the data, or we can reference it directly from Mongo as we need it.
Mm-hmm. So the subject of this discussion is going to be visual search and how to build a visual search engine. But before we get there, what are some of the search challenges across Squarespace? Like, is there a set of search problems that the organization of the product has?
Yeah, so we have millions of websites on Squarespace, right? So the problem we sort of have as a company is, how are people using the product? Speaking about visual search specifically, like you mentioned originally, Squarespace is a very design-heavy company. So the deal basically is or a visually design-heavy company. So the question for us is, how do people use our templates and our CMS to build out their website? So how does it look, basically? So you can sort of do queries to get that information once we pull out the aggregated information. And you can see, okay, something like people are using this kind of template, or people are using like this other kind of template. Like, you can see all the list of templates on squarespace.com if you're interested. But the problem is you can't get really detailed in how you view in exploring different visual designs of our customers. So what we were thinking about ways to essentially explore styles on squarespace.com, the styles of our customers. And one sort of idea we had was, why don't we take screenshots of every single website and and use those screenshots and to build a visual search engine so that we can sort of explore sites there. So the idea was a totally new way to search Squarespace sites visually, so you can find styles that you cannot possibly find by just querying the HTML or just querying the text on a website.
Mm-hmm. Is the problem essentially building a search index where you can submit an image and get images that are somehow related to that image?
Yeah, exactly. That's what the entire idea is. So if you've used probably the most popular visual search engine around is the Google search engine, Google's image search engine. You can basically just click on, I think, like images and you say upload your own image and you'll find like similar images across the web. Probably a lot of people are familiar with that product. So ours works essentially the same way. Mostly people I don't think we've actually released the feature where you can upload your own image yet, but we basically allow people to explore similar images or similar websites. So you basically type in, like squarespace.com into our visual search engine and we'll find other websites for you among our customer set that look like that one. But the technology is pretty much exactly the same. It just goes through the same flow.
The plan to build this visual search engine is first you have to get the data to search. And you already kind of talked about that, crawling the websites or just taking snapshots of all the different websites on Squarespace. And then after you have that data, you train a machine learning model to make that data searchable. And then you build a search index. So given that we talked about that first stage, you wrote the script to go to each site on Squarespace and take a screen capture. I like that hack because it's like, I guess there wasn't an index of these images readily available. Like you would think, oh, okay, this data is kind of structured because we you could just crawl the HTML of each of these sites and pull those images, but instead you went and you just did a screen capture of each page on Squarespace. Can you talk about those two contrasting approaches, why you went with the screen capture instead of crawling the raw HTML?
Because like I was saying, for example, so firstly, I actually didn't scrape the images myself. It was actually our head of data engineering who thought of this was a neat hack to do it using a headless Chrome instance, actually. But the main reason we wanted the images themselves is because we wanted to be able to allow people. We wanted to allow people to search visually. So if you just crawl the HTML and you can't really see, you don't really have the most accurate representation of what the site is. You have to basically load the site, and then you basically have to load the web page, the front page, and then somehow manipulate that raw text HTML to make it visually queryable, which I don't think is even easily doable. So our idea was, why don't we just load it as people see it so that people can use images or look at related visual content. I guess the contrasting approach is mostly about what we thought would be better for our users. And I think the way we approached it was we wanted to let people search the way they actually view a website. Because when you go to a website, you're not actually looking at the HTML, you're looking at it, just looking at a screen, right? So that was our theory, basically.
So does that mean that if is the goal, the high level goal of this search engine, you submit an image and then it is comparing that image to all of the different websites across Squarespace? Because I thought that what you would want to do is you want to find, I want to submit an image of this cat because I want to find other cat pictures that look like they would be a good fit for my, cat collage page on Squarespace. So maybe you could just talk a little bit more about the high-level goal of this visual search index.
Right. Okay. So the high-level goal is basically to let our designers and marketers and anyone at the company find visual styles on Squarespace. So this particular search engine is for that purpose. So it's purely for screenshots of the front pages of websites. So you're trying to find what websites on squarespace.com have the same visual style as my website or this other website or whatever query website you have. Your case, the one you're talking about, where finding similar images that I want to put on that I may want to add to my website, like cats, you submit a cat image and you want to find other similar looking cats that you can add to your website. That is also possible with this same sort of pipeline. In our case, we made a specific model. We basically trained our own deep learning model to turn these screenshots into something searchable, like vectors in our case. So we would essentially train a model for the cats situation, or for arbitrary images, we would train another model for that purpose. So it's essentially the same flow, but this specific search engine is not meant for finding similar like cat images. It's meant for comparing websites themselves.
Yeah. Well, and I suppose two things. One, Google already takes care of that problem pretty effectively, and two, I kind of understand, given what you've said so far. So somebody goes to Squarespace and they're like, well, okay, there's so many different designs I could use, and I wish I just had a way to look through all the different ways that people lay out their websites, because there's it's such a flexible tool. You can lay out the design of your website in so many different ways. How do you build? That makes it a much more interesting problem. It's not how do I find specific images, it's how do I find page layouts that would be palatable for me.
Right. Mm-hmm. So our customers don't actually have access to the tool yet, but it's possible we'll release something like that later on.
Grammatech Code Sonar helps development teams improve code quality with static analysis. It helps flag issues early in the development process, allowing developers to release better code faster. Code Sonar can easily be integrated into any development process. Code Sonar performs advanced static analysis of C, C++, Java, and even raw binary code. Code Sonar performs unique data flow and symbolic execution analysis to aggressively scan for problems in your code. Just like battleships use sonar to detect objects deep underwater, engineers use Code Sonar to detect subtle problems deep within their code. Go to go.grammatech.com/sedaily to get your free 30-day trial exclusively for Software Engineering Daily listeners. Code Sonar analyzes your code, and it delivers a detailed report. The Code Sonar user interface provides all the information that you need to quickly understand the reports, follow cross-functional paths, understand cross-references, quickly navigate between files, and visualize large pieces of your code. Go to go.grammatech.com/sedaily to get your 30-day free trial and unleash the power of advanced static analysis. Thanks to Grammatech for being a sponsor of Software Engineering Daily. Well, okay, so let's start to talk about the guts of the machine learning problem, how you were solving it. Okay, so you have this index, you have this data set of screen captures, basically a screen capture of every website on Squarespace. And you had to downsize these images in order to feed them into a GPU. So explain why that is.
These images are actually really large. So I think we take them something like 900 by 1300 pixels. So that's actually quite a bit of data. And I think there's several hundred gigabytes or possibly even terabytes of images, like raw screen captures that we could have used. The problem with that is in order to use our approach was to use essentially a convolutional model. And so in order to use this deep learning model, you really need to downsize those images to make it even manageable. Otherwise, the neural network is just way too large. So what we essentially had to do is pick a reasonable sized image size that still allowed the model to understand what was actually going on in the image. If you take it too small, if you switch those screen captures to 4 by 4 pixels or something, that's way too small. And then obviously there's nothing to learn from there. So in our case, we chose 64 by 64 by 3 for color images, the 3s for RGB. So in our case, 64 by 64 by 3 was more than enough to really capture all the features of an image. So basically, we just downsized all of these giant images to that size in order to sort of make it more manageable and make the convolutional neural net a little bit smaller and more trainable. So when you put it on a GPU, for instance, to explain it another way, the GPU has a limited memory size. So I think the GPU I was using at that point was only like 4 gigabytes. It was an Amazon EC2 instance, and it's like one of the G2 instances. So pretty small GPU, only 4 gigabytes. So basically, if you wanted to use the raw images, I don't think they would really have fit. Like you couldn't have really trained very quickly with those with the raw image sizes there. So in our case, we squished the images pretty dramatically, and we were able to essentially shove them in the GPU. So there's like a capacity problem you have to worry about when you're doing these deep learning models.
And it sounds like you weren't downsizing them so much that it was lossy, or not very lossy.
No, not at all.
Yeah.
So basically, you have to choose that size somewhat carefully. And if you go too small, then you can't see anything in the image, right? Like 4 pixels by 4 pixels is like too small, but 64 by 64, that's big enough. And obviously, like 256 by 256 or 1000 by 1000 is way more than enough. So you sort of have to choose the size yourself. There's not much to help you there in tooling. You essentially just have to choose it yourself and say, like, this image is basically large enough that we can make out features inside of it, and small enough that we can still train the model effectively.
We did a show a while ago with Vasco Pedro from Unbabel, and he was talking about how the AWS GPUs, or he might have been talking about Google Cloud's, whatever they have available for machine learning, that were not good enough to do the kind of machine learning jobs they wanted to do. Did these AWS GPUs, did they recently get good enough for training, or is this just maybe not a super intense problem compared to how intense certain problems can get?
Oh, so certain problems can get extremely intense. It depends, obviously, on the problem. The GPUs that we were using have actually been around for quite a few years. I know they were definitely around 3 years ago, and they were definitely around a year ago. So Amazon actually just added a bunch of pretty high quality GPUs just recently, I think possibly in the last year. But they basically had to do that, I think, because Azure, like the Microsoft Azure cloud, and I think also Google started allowing GPUs, maybe only in beta testing, but that were much more powerful than Amazon. So they essentially had to catch up. But the GPU for our case was more than enough. This problem is pretty intensive, but it's not necessarily like overwhelming. And the deal is with those GPUs, what you can essentially do with all of these deep learning models nowadays is distribute them across as many GPUs as you want. So if you look at TensorFlow, or you've looked at TensorFlow kind of grow and expand over the past, I guess, a year and a half now, basically a lot of the work has been in distributed training of models. So what they'll basically do is not just use one server. They'll use multiple servers that are ideally close together and physically, and distribute the model across all of those servers. And they can essentially do that in two ways. One, they can have copies of the model on individual servers and sort of distribute the data across those different servers, or they can actually distribute the model itself across all of those servers. So if you have a giant model, you can distribute it across all these different servers. You can break it apart and put it on different servers, or you can distribute your data and try to speed up your training time, sort of. So it sounds like in the case you're describing, whatever problem they were doing was much more intensive than ours. So if you're not willing to spend so much money, then the Amazon GPUs can get kind of unwieldy for you. They're about 65 cents an hour if you want them on demand. So pretty expensive if you're trying to use them for like months or weeks or even at a time, you know.
Right. Okay. So this is kind of like a constant time operation for you, because you don't have to do this training like over and over and over again. I mean, theoretically, you would want to do it on the fly for every new website that was built, but probably not a huge deal if you don't do it more than, once a month or even once a year. And that's really interesting what you said about the distributed deep learning stuff. We did a show about that, about this model distribution versus the data distribution. And that show went, like, a lot of the content in there went really over my head. It sounded like, because the distributed systems problems, like at the intersection of distributed systems and machine learning, are some pretty complicated things. But does TensorFlow kind of abstract away a lot of that complication?
Yeah, my personal opinion is no, not at all.
Oh,
I mean, you can definitely do it, and I was able to distribute some modeling work, some models like I guess like a year ago, even when I was using it, and that was not even that was not even the 1.0 version of TensorFlow. It gets better so quickly because I think Google has a lot of people working on it, and it's open source, obviously, so a lot of people are contributing to it. And I don't think it makes it that easy. Their documentation was not particularly good about a year ago. Recently, it's gotten a good bit better, but originally, it was not so easy to get things distributed. But you're totally right, though, to answer or to talk about your second point that it's very complicated and a lot of people are contributing to it. I think even very recently, I think Baidu Research actually even came out with a new type of message passing algorithm that you can basically plug into TensorFlow that was meant to just speed it up a little bit. So a lot of different people are working on a bunch of different pieces of this distributed model training that to try to make TensorFlow even faster, or even, I guess, the other major deep learning frameworks.
Baidu is contributing to TensorFlow? That's kind of surprising.
Yeah, I can look it up for you, the exact algorithm. I forget what they called it, but they basically released some library that makes distributed training a decent bit faster using some message passing interface algorithm.
Yeah. Well, that's all right. I can look it up later, but that's kind of actually nice to hear. From my perspective, I hate seeing the tech titans. Well, in some sense, I like seeing them battle each other, but seeing them contribute to each other's projects is perhaps more exciting.
Right.
Anybody who has listened to a previous episode of Software Engineering Daily about search knows that this is a problem where you have to build vector representations of images or text or whatever you're searching over, in most search engines at least. So these vectors allow you to do similarity comparisons. So if somebody does a query, you can measure the similarity between the query and the corpus that you are searching. So I guess let's start to talk about that, because for each of these images, you're going to need to build a vector for it. How do you encode an image into an easy-to-search format?
Right. That's exactly correct. Kudos on that understanding. Basically, the entire idea is to take these data sets, be it text or audio or video or images in our case, and convert them into some space which you can then search. So the easiest way to think about it broadly is you literally just take an image and convert it to a 2D space, like an XY coordinate, just like any graph you've ever seen in your life. And you can just dump all of these images onto a graph via some machine learning model, and then you can literally just use nearest neighbors at that point, being like, what is the nearest point to this one image point that I've transformed. So the way we do it is we use a fairly new, I guess, technology or type of machine learning called deep learning. And that, I guess, it's been fairly popular now for the last 5 years. Most of the major advances you've seen, I guess, are probably due to this deep learning stuff. And the specific model that we're using is called a convolutional variational autoencoder. And this model basically works by taking in some input, some image, and recreating that image on the other side of the model. And in the middle of the model, the meat of the model, what you're basically doing is squishing the image repeatedly until it squishes down into a vector, and then you blow it back up into the original image. So it's sort of like a reconstruction problem where the middle of the model is this vector. So I hope I'm explaining this correctly to you. So you pass in some 64 by 64 by 3 image, you repeatedly squish it, it turns into like a vector, and then you blow that vector back up. So that vector, the middle vector, is sort of a byproduct of this entire problem, but what you can do is use that as a searchable you can use that as your searchable format. So once you plot that image, then you can do nearest neighbors on it. But in our case, yeah, so this specialized model that we trained ourselves works for that purpose.
Right. So if I know this problem correctly, this multi-layer deep learning network, at the lowest layers, you have convolutional layers, which are doing things like building up edges, building up these lower level representations of images. You just say, okay, well, here's an edge, here's a collection of edges, and then in the middle layers you're building up slightly higher level abstractions that are identifying things that a set of edges aggregate to, these higher level abstractions. And then over time, the higher and higher levels, you get higher and higher abstractions. The human may or may not be able to understand what the computer is seeing across these abstractions. That's one of the things that makes this area so interesting, is the way that we're teaching computers to see images feels a lot different than how we perceive images. And at each of these layers, you've got a slightly different representation of that image from the computer's point of view. So at the very lowest levels, it's like, okay, this image is a set of edges. The middle levels, you're like, okay, this image is, a set of like shapes or colors, or I'm not explaining this super well, but eventually you get to the highest level and it's like, okay, these edges aggregate into some blurry shapes. These shapes aggregate into a cat. And at the highest level you have, okay, this is a 90% chance there's a cat in this picture. Am I portraying the layers correctly?
Yeah, I think that's an interesting way to think about it. The way I think about it, for example, for this model that we're doing specifically, is outer and inner layers. So it's a little easier than saying higher and lower, because the model that we're using, for example, it's basically like a multiple layers with the middle layer, and then middle layer, which is our vectors, and then it blows it back up again. So like the way I think about it is somewhat similar to that. Yeah. So it's essentially these deep learning models are building like what most people call hierarchical representations. So the outermost layers are looking up high-level features, and the innermost layers are looking up really detailed low-level features. So you're basically building this hierarchical representation of your data sets. And basically these new deep learning models have so many layers that they have millions upon millions of parameters. One of the most recent models that Google released to the world, a pre-trained model, I think has like 130 million parameters, which is enormous, really, if you think about it. When you first learn about machine learning and you're learning how to use, for example, a simple model like logistic regression, you might only have like 20 parameters in your model, and these things have like hundreds of millions of parameters that people are using in the wild. And so all these like different layers are basically contain enormous numbers of these parameters, and the outermost layers are sort of learning a little bit of the high-level abstract features of the image, and then you sort of get successively more specialized as you go inward into the model. So like essentially similar concepts to what you're describing, but yeah, I think about it more as like outer and inner layers. But yeah.
You mentioned this term autoencoder. Can you explain what an autoencoder is?
Right. An autoencoder is basically exactly what I was talking about. The entire idea is to take some piece of data, and we can, I guess, use images since we've been talking about that, and pass it to this model and get essentially the same model out on the outside. So the idea is same image out on the outside. So it's basically the autoencoder basically does what's called a reconstruction. So what you're doing is you pass in some image X, and on the outside of it, you should get X prime back, and X prime should be as close to X as possible. So what the autoencoder does in the middle, like the meat of the autoencoder, it's basically successfully squishing the image down into some format that you're interested in. And usually people are interested in vectors. So this is basically the exact problem that we're dealing with right now. So it's usually one of the first introductions people have to deep learning or neural networks, because it's somewhat easy to understand. You pass in something and it squishes it down into some simple vector format, and then it blows it back up again into the exact same value. So when you pass in millions and millions of images, for example, into these autoencoders, what they're supposed to do is learn how to squish the input image into a vector and then reconstruct the input image from that vector. So what should happen is when you pass in millions of images through this thing, what should happen is the vectors should be very, very good representations of the image. Mm-hmm.
And the final output of this neural network is going to be some sort of vector that you can search against. Basically, the vector that you're going to want to do similarity measurements against the query, whatever the query vector is. And from what I know, you can take values from each of these layers if you want to. You can basically at any of these different representations, they're not exactly the same. So, or from the inner to the outer layers, you could theoretically take as many of the parameters from the middle layers and put them into the output vector as you wanted to. And to some degree, that would add a higher degree of granularity to those final vectors. Tell me if I'm correct, and then tell me like what, if I'm correct, what layers you want to actually pull data from and put into the output vector.
Yeah, so you're entirely correct. Each different layer's output, you can use as an intermediate representation. It sort of depends on what you're looking for in your model. So I can explain this to you sort of in two separate ways. So in our case, when we're building our convolutional variational autoencoder, we want the middle layer, and that's basically it. We want the exact middle vector layer. You can use the other outside layers, the outer layers, outputs, but the middle layer, which gives us our exact vector that we're looking for specifically, so we can plot it and everything is the same, and it's like nice small vector too. It's only like 256 elements long. We want to use that specifically. But in a lot of different cases, people will use higher up feature, the output of higher up layers. So for example, you've probably heard of all these neural networks that are typically used to classify like things like images into like 1,000 categories. Like, is this a cat image, or is this like a boat image, or is this like a dog image, or whatever else? So this problem is slightly different than the one I'm describing when we're building a search engine, where you're building an end-to-end classifier. You're passing in images and you're basically running them through this giant deep neural network, and the output is basically a probability for, or like a category, a specific class. But that model works very similarly to our variational or our autoencoder, in that each layer has an output that you can use for specific other tasks. So a lot of people will use, for example, the same Google model that I was describing earlier, that is like this pretty powerful classifier for very different tasks. So the idea is sort of like transfer learning. So what you're basically doing is you take whatever Google's pre-trained model is, and then you pass an image through it, and you take one of the higher level of the output, the outer layers outputs, and you can use that for whatever other tasks you want. So if you have some other data set that you're trying to classify, but you don't have too many labels, you can pass it through this giant classifier model, take one of the outer layers outputs, and then use that as input to your secondary model. I hope that makes sense. I don't know if I'm explaining this correctly.
No, it does make sense.
Yeah, so basically like the idea is like these deep learning models learn all these hierarchical representations. So the output of each individual layer like is useful for some purpose. May not be like practical for your specific purpose, but some purpose can. There's probably some purpose where it's useful for you.
Who do you use for log management? I want to tell you about Scalar, the first purpose-built log management tool on the market. Most tools on the market utilize text indexing search, and this is great for indexing a book, for example. But if you want to search logs at scale, fast, it breaks down. Scalar built their own database from scratch, and the system is fast. Most of the searches take less than a second. In fact, 99% of the queries execute in less than a second. That's why companies like OkCupid and Giphy and Career Builder use Scalar to build their log management systems. You can try it today, free, for 90 days if you go to the promo URL, which is softwareengineeringdaily.com/scalar. SCALYR. That's softwareengineeringdaily.com/scalar. Scalar was built by one of the founders of Writely, which is the company that became Google Docs. And if you know anything about Google Docs history, it was quite transformational when the product came out. This was a consumer-grade UI product that solved many distributed systems problems and had great scalability, which is why it turned into Google Docs. And so the founder of Writely is now turning his focus to log management. And it has the consumer-grade UI. It has the scalability that you would expect from somebody who built Google Docs. And you can use Scalar to monitor key metrics. You can use it to trigger alerts. It's got integration with PagerDuty. And it's really easy to use. It's really lightning fast, and you can get a free 90-day trial by signing up at softwareengineeringdaily.com/SCALYR, softwareengineeringdaily.com/scalar. And I really recommend trying it out. I've heard from multiple companies on the show that they use Scalar, and it's been a real differentiator for them. So check out Scalar, and thanks to Scalar for being a new sponsor of Software Engineering Daily. once you have these vector representations, you are able to treat visual search as a k-nearest neighbor problem, which is where you can find the k-nearest neighbors to a given vector. If you want to find the 5 closest neighbors, you can do that, and so on. Describe how this is applicable to building a search index.
Basically, the end-to-end idea is you take images, you convert them into vectors, and then you find similar vectors for the search. So the end-to-end problem is literally just take some image, stick it in some subspace, and then in that subspace, you can just explore around whatever input vector you have, input image you have to find similar images. So the idea is sort of like to convert, like to take this like high-level idea of like use of a visual search engine where you like stick an image into this search engine and you get back similar images and convert it to this like simple numeric problem of finding nearest neighbors. So it's the idea is sort of so the entire sort of procedure is in 2 parts, right? You need to encode your images into this subspace and get vectors back, and then use those vectors, and then search that subspaces of vectors. So in our case, we were doing exactly what you described. We were using KNearest Neighbors, but since we have so many images, like several million images, we have several million vectors. And so if you're familiar with how to do nearest neighbors problems, you'll realize that if you want to do a brute force search across all those vectors, it's just way too long. It'll take like, I guess, n squared time. You need to compare each vector to every other vector. So that's just not really viable. So we're not the first person to have discovered that problem. Many other people have in a bunch of different companies and research organizations. So they came up with this idea of approximate nearest neighbors. So 2 of the most famous libraries that you can use for that are Annoy, which is built at Spotify, and then I'm not sure how to say it, Face, F-A-I-S-S, which was built at Facebook, and that's a relatively new library, I believe. Mm-hmm. But both of these two libraries or techniques are effectively very similar, but they allow you to sort of search this subspace in very fast time. So to go back to your original question of how does k-nearest neighbors relate to visual search, the entire idea is literally to convert an image into a vector and then look at similar vectors and numerically compare these vectors, and that's literally the search engine at the end of the day.
I talked to the guy who worked on however you pronounce Facebook, like AI search series or something. I don't know, FAISS, I think, or FAIS. I talked to that guy who built that. It's funny because that interview was like so similar to this one that we're doing right now. It was just, for images across Facebook, which is a slightly different domain, but very similar problem. Why is that? Why is it that Facebook and Squarespace and probably a bunch of other companies are solving this same problem? Is this just like a canonical problem that we've had for a while, and like all of a sudden we have the tools to deal with it?
I think so, yeah. So if you think about like the problem, this visual search problem, or just this general search problem using these techniques, you sort of see like you basically break it into 2 parts, right? You need to convert some piece of data into a vector, and then you need to use these approximate nearest neighbor vector search techniques, right? So the key is, there's actually 2 keys there, but the first part is like the encoding process. And until recently, there wasn't really an excellent way to encode images and encode text. So deep learning sort of took off about 5 years ago now. I think it started sort of booming in 2012 with the release of, I think, this convolutional classifier by I forget how to exactly say his name. I think his name is Alex Krzyzewski. But yeah, I mean, he made sort of like a seminal paper using convolutional neural nets. And ever since then, people have been using deep learning for everything. And until, I guess, 2012, like I'm saying, there wasn't really a great way to encode vectors, or encode text and audio and video and image data into vectors. So until recently, I guess, people didn't have a great way to do it. And now that people do have a great way to do this problem, everyone's using very similar techniques. To sort of talk about like why different companies are doing such similar stuff. The machine learning community is not really that massive, in my opinion. The reality is everyone talks to everyone else. And if you go on Twitter, you can follow any number of machine learning researchers who constantly talk about what they're doing. Everything's available on GitHub now. There's so many giant conferences everywhere that all the researchers go to, or they just view the casts for, or they join online even sometimes. So just everyone's talking to everyone. It's just like a booming field right now. So I think there's a lot of like, not necessarily groupthink, but a lot of sort of similar style of work in the field. That's my take, at least.
And my feeling is that there's this open source world of some machine learning technologies, and then there's some stuff that must be going on behind the scenes at DeepMind or in the darker regions of Facebook's AI department. And this is where the real intense like competition and the hidden stuff is going on. Do you think that's true? Like, is there's this large, probably, like stuff? I mean, how far DeepMind, for example, like how far ahead of the curve do you think DeepMind is relative to what the open source community is privy to?
Yeah, that's like a hard question. I'm not entirely sure how sort of advanced they are these days. I mean, so they've also been focused on a sort of, some people say it's a subfield of machine learning, and some people say it's it's like sort of a more broad field of machine learning, this other thing called reinforcement learning.
Right.
So they've been very recently very much looking at that. If you go to the conferences, they basically dominate a lot of them. If you go to, for example, I think this past year I went to these two large conferences, NIPS in Barcelona and then ICML, which was in New York. And they're two giant machine learning conferences. And basically DeepMind and Google at large is pretty much like all over those conferences, much more so than I think pretty much any of the other large companies. And you can literally just go onto those conference website pages and you can see like how many papers those companies are actually putting out. But I'm saying this basically to sort of talk about how I don't know if they're keeping much secret. They probably have a lot of unreleased papers, but they seem to be very interested in sort of dumping and sort of putting their research out into the real world so other people can use it. I don't know if they're keeping it to themselves. That said, their research is extremely advanced and they have access to computational power that, for example, that Squarespace doesn't really have, right? You have all of Google's power and money to sort of do whatever research you want. So they basically can run experiments that other people can't really run. So yeah, I mean, a lot of it is simply just due to that they can afford to do this kind of work using just massive numbers of GPUs, massive numbers of storage, a massive amount of storage, and just massive numbers of CPUs as well.
Not only that, but they have a team structure that nobody else can replicate, where they have this team structure where, like, okay, the team consists of like 4 research leads or 2 or 3 research leads, and then like a number of research engineers, and everybody's got a PhD. And it's like, whoa, even if you told everybody what your strategy, nobody would be able to replicate you, because it's just like they have so much of an advantage there, which makes them so interesting. And from that point of view, why wouldn't you just like publish everything and see what the open source community takes off with, and see what ideas they come up with, and then you can, if you're DeepMind, you can just come back and put take whatever the open source community gives you. If you're so ahead resource wise, you might as well just publish everything.
Right. Yeah.
So I know we've gotten away from the visual search, but I just want to ask, like, so the focus on reinforcement learning. Now, deep learning together with reinforcement learning, this is something I've tried to do a little coverage of. Is the reason that that's so potent because with like kind of deep learning, just if we're talking about deep learning with the type of image classification stuff that we're talking about here with building the search index, that is supervised learning. And with reinforcement learning, you get towards something that is a little more like unsupervised learning, because you're just giving it a reward function to optimize, and it figures out all of the ambient parameters and other stuff that's going on there. Am I overstating the truth, or is that kind of the motivation for going after reinforcement learning?
Yeah, that's a good way to put it, I guess. So I guess the autoencoders are unsupervised, actually, but the classifiers, like the image classification tasks, are very much supervised. So reinforcement learning, I guess you could broadly think of it as unsupervised learning. I don't know if most people specifically like think of it that way, though. If you like asked a researcher in that field, they might say like, it's not really unsupervised learning, but it's sort of like a semantic, like different people have different opinions. The terms are so broad that people have different ways of thinking about the problem. But yeah, I mean, I guess reinforcement learning like is pretty much unsupervised, broadly speaking. But at the same time, there is a reward function, right? So you're trying to reach something. With unsupervised learning, there's not really a specific task. So it sort of exists in this like yes and no weirdo space that it's not really like easily defined. But people think it's very, very powerful. And obviously it's proven powerful at, I guess, solving a lot of games like Go, for example, like beating some of the greatest players ever. But I guess it's unclear. I don't know how many people have used it for other real-world tasks just yet.
Yeah. Well, I guess it's supervised, but it's or it can be supervised, but all you have to define is the reward function, and all the labeling you would have to do would be based around verifying that reward function. So maybe it just, I don't know. It's for another show. So I know our time is drawing short, and I want to put a bow around this problem that we've kind of outlined. So this visual search index that we've built, now take us from there to conclusion. Like, what else do we need to know about the rest of this project, and how is this visual search index being used right now?
Yeah, so I guess for actually building the project, I guess I never mentioned the tool, so maybe I'll do that really quickly.
Oh, of course, yes.
Right, yeah. So we use KNearest on top of TensorFlow. KNearest is a very popular library for building deep learning models. Our compute framework is Luigi. It's like a job framework really built at Spotify. Our index or search index is built in Annoy, another technology taken from Spotify. So that's the approximate nearest neighbors index. I guess we use Spark for whatever distributed processing we need for the same project, and see what else we need. I guess Spark with Hadoop as well. And I guess all of our hardware for this particular problem was actually done on EC2 for the research and the actual development using their G2 instances on there. So that's like the tools that we used. But I guess like for what else are you asking? So what is what else do you need to know about how it's being used internally? So basically, the way most people at Squarespace use the visual search feature is to sort of browse websites. So what you're trying to do is take some image, what you're trying to do is find some visual styles. And if you find a visual style that you think is interesting, then essentially, if you're a designer, for example, you might build a new template that represents that style. So basically, to essentially like fill gaps in our template designs. So that's one thing that you could do if you're a designer at Squarespace. If you're like if you're someone like a marketer, then what you could do is look at these websites as well and try to find interesting ways people are using our sites by finding similar visual styles and basically saying, okay, so this is like a feature we should promote because a lot of people seem to be using this style. So those are like two, for example, ways that you could use it. But yeah, we have some other things in the pipeline, but yeah, right now those are the two, I guess, two examples for you. Use it.
Okay, well, I guess to wrap that up, since you mentioned you have some things in the pipeline, are you talking about using the same machine learning stuff you've already built up for the purposes of this visual search, or are you building something new? Maybe you could give a little color on what's in the future.
So I can't talk about what's in the future yet, unfortunately, but sorry about that. But we have some other features and products we're planning on using the same technology for. But yeah, I don't think I'm allowed to say the exact features we're building.
No problem. There's always more shows in the future.
Yeah.
Cool. All right. Well, Neel, it's been great talking to you, and it's really interesting hearing this same problem solved. I think when you listen to this episode, it's going to be, I think I'm going to publish it the day after I publish the Facebook one, or I'm going to try to get them, closely aligned with one another. And it's always interesting, doing two shows about an implementation that two different companies have tried to do and kind of seeing the similarities and the differences in approach, and just like the fact that, the industry gestalt is such that multiple people are working on this problem. It's surprisingly fun to do multiple shows about almost the exact same problem being solved. So thanks for indulging me.
Oh, no, sure, of course.
Wonderful. Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!